All right, here's a wild thought for you. Have you ever wondered if a single liquid could have two different voices? I know, it sounds like some kind of riddle, but believe it or not, it's a real phenomenon that takes us straight into the bizarre and totally fascinating world of quantum mechanics.
So let's just jump right in. Can a fluid have two sounds at the same time? It feels like the answer should be a hard no, right? But in the quantum world, the rules are different. And the answer is a definitive yes.
Okay, so take a look at this. This awesome illustration kind of gives us the first clue. We're talking about something called a quantum fluid, or a superfluid. And you can think of it as two liquids all mixed up together. You've got your normal fluid part, and then you've got this superfluid part that flows with absolutely zero friction. It's wild. Now, look at the top diagram. That's first sound. It's basically just normal sound, a pressure wave. See how all the particles are bunched up, moving together? That's what physicists call in phase. But then, look at the bottom. That's second sound. This is where it gets weird. Here, the two fluid parts are moving against each other. They're out of phase. And this isn't a wave of pressure, it's a wave of temperature.
So, in this explainer, we're going to unpack this whole quantum duet. We'll get into what these two sounds really are, how scientists even found them, and why one of them, well, it turns out to be a huge deal for understanding the quantum world.
Yeah, see, finding this second sound isn't just some neat party trick for physicists. It's way more important than that. Finding it is the absolute definitive proof. It's the smoking gun, the telltale signature that proves you're looking at a real deal quantum superfluid.
But hey, let's back up for just a second. What even is superfluidity? Well, it's this super exotic state of matter where a part of the liquid has zero viscosity. I mean zero, no friction whatsoever. This stuff can literally climb up the walls of its container and flow through cracks that are impossibly small. It does things that normal fluids, they just can't do.
Okay, this right here really gets to the core of it. First sound, that's basically the sound you're used to. It's a density wave, a pressure wave, no big deal. But second sound, man, that is something else entirely. It's a wave of temperature. Think about that. Instead of pressure going up and down, it's the actual heat that's waving through the liquid. You'll never see that in your morning coffee, right? It's a purely quantum thing, and it only happens because those two fluid components are sort of sloshing back and forth against each other.
And this quote just nails it. This is exactly why scientists spent decades hunting for this thing. Finding second sound isn't just about hearing some weird quantum echo. It's the one unambiguous, can't argue with it piece of evidence that tells you, yes, you've done it. You've created a superfluid.
You know, this idea has been around for a while. It's got this really cool history. It all started way back in 1938 with a prediction from a physicist named Laszlo Tisza. A few years later, the legendary Lev Landau came along and gave it this rock-solid theoretical backbone. And then, the big moment. In 1944, a guy named Vasily Peshkov actually did it. He managed to detect this bizarre temperature wave in super-chilled liquid helium.
Okay, so, mission accomplished in liquid helium, right? But scientists being scientists, they immediately asked, okay, what's next? Can we find this somewhere else? And that set up the next great challenge, hunting for second sound in a totally different and arguably even weirder kind of superfluid.
So the new frontier was something called an ultracold atomic gas. And just try to picture this. You take a cloud of atoms and you chill it down to temperatures colder than the deepest parts of outer space. We're talking a tiny, tiny fraction of a degree above absolute zero. And when you get things that cold, the atoms they start to act as one, forming this brand new type of superfluid. And here's the cool part. These aren't just lab toys. They're like little model universes that can help us figure out some of the biggest mysteries out there, from what's going on inside neutron stars to how high-temperature superconductors work.
But, man, this was so difficult. For decades, it was this elusive goal that physicists just couldn't quite reach. For one thing, the magnetic traps they used to hold these atom clouds, they just made the physics super complicated. And even worse, the theories all predicted that this temperature wave, this second sound, would barely even make a ripple in the gas's density. So it was basically invisible. I mean, how do you even begin to look for a wave you can't see?
Then, in 2009, a breakthrough. A theoretical paper came out, and it gave everyone a glimmer of hope. It basically said, okay, look, the signal is going to be incredibly weak, but there's a trick. Because second sound moves so slowly, its effect on the density actually gets amplified a little bit. It would be faint, but maybe, just maybe, you could see it. And that was the crucial clue the experimentalists have been waiting for.
And that insight really set the stage for a landmark experiment that happened in 2013. a team at the University of Innsbruck decided they were going to go for it. They were finally going to try and catch a glimpse of this invisible wave.
And their method was it was so clever. First, they trapped this tiny cigar-shaped cloud of super-cold lithium atoms. To make the first sound, they literally just gave the cloud's center a sharp poke with a laser beam. Simple enough. But for the second sound, they did something way more subtle. They gently heated the center with a really fast pulsing laser. The whole point was to create a temperature wave without really disturbing the whole cloud. And then they just took pictures and watched to see what happened.
And this is the aha moment. This is what they saw in the pictures. The sharp poke, it created two little humps of density that shot outwards, exactly what you'd expect for normal sound. But the gentle heating, that created something incredible. It created two propagating dips in the density. Not humps, but dips. It was like a hole, a traveling cold spot that moved slowly outward and then just stopped right where the superfluid part ended. They had done it. They had made the invisible temperature wave visible.
And the researchers themselves, in their paper, they called it perfectly. They said this behavior is our smoking gun. This moving dip, this cold spot, this was the definitive proof they've been looking for decades. They had finally found it.
So you might be thinking, okay, that's cool, but why is it such a big deal? Well, it matters a lot. Because finding second sound wasn't just about ticking a box and saying, yep, it exists. It actually unlocked a whole new toolkit, a new way to measure the most fundamental properties of these quantum materials.
You see, here's the thing. The theory said that the speed of that temperature wave, it's like a speedometer for the quantum state of the material. It's directly tied to this super important number called the superfluid fraction. And that's basically just asking, what percentage of this gas is actually in that perfect, frictionless superfluid state? It's like a purity test. And before this experiment, that number was almost impossible to get your hands on.
And the results they got were just stunning. By measuring how fast those little dips moved, they could calculate the superfluid fraction. And what they found was that once they got it cold enough, their gas was nearly 100% superfluid. I mean, look at this chart. It behaved almost exactly like the classic liquid helium that started this whole story, and it was totally different from other kinds of quantum gases. Just incredible.
This one measurement, it was like finding the Rosetta Stone for these quantum systems. Seriously. It was the missing piece of the puzzle for this grand theory, this sort of universal rule book that describes how all these exotic quantum gases work. And that means scientists can now better predict what's going on in other systems they can't just build in a lab. You know, like the insane, ultra-dense stuff that makes up a neutron star.
So really, finding second sound wasn't the end of a long search. In a way, it was the beginning of a whole new conversation. By finally figuring out how to hear both voices of this quantum fluid, scientists have this powerful new tool to listen in on the strange and wonderful duet happening right at the heart of matter. And that leaves us with this really tantalizing question. Now that we can finally listen in, what other secrets is the quantum world going to tell us?